Welcome to another physics revision video. This video is all about beta decay. Radioactive isotopes are unstable and so they decay. They change into a different nucleus, releasing energy and radioactive particles. Take a look at this graph carefully. It shows you the number of protons against the number of neutrons for lots of different isotopes. The ones in black causing the curving best line are the stable isotopes. They're not radioactive, but all of the other parts of this graph, or the coloured shaded parts of this graph, are showing radioactive isotopes and the way in which they decay, the type of radioactive particle that they emit during that decay. In this video, I'm only going to focus on radioisotopes with less than 82 protons. I'm going to focus only on beta decay, but we are going to look at both beta minus decay, which emits electrons, and beta plus decay that emits positrons. Above the curve that's formed by these stable isotopes, we find radioisotopes that have too many of these guys. They have too many neutrons. You can see on the graph from the lack of purple colour that there aren't many radioisotopes that can just kick out a neutron to help them get more stable. More commonly, isotopes that have too many neutrons to be stable become stable by changing one of those neutrons into a proton. Doing this brings them closer to that curve of stability, closer to being a new, stable isotope. So, radioisotopes found above the curve of stability become more stable by changing a neutron in the nucleus into a proton, which also stays in the nucleus of the new isotope that's made. To explain how a neutron becomes a proton, we need to introduce these guys, our up and down quarks. Protons and neutrons are in a group of particles called the hadrons. Unlike the electron, which can't be broken down into anything simpler, protons and neutrons are not fundamental particles, and that is because they are made up from quarks. Protons are made from 2 up quarks and 1 down quark, where neutrons are made from 2 down quarks and 1 up. So when a neutron changes into a proton, what's actually happening is 1 down quark is changing flavour to an up quark, and this all happens inside the nucleus of that unstable radioactive isotope. Now both up quarks and down quarks have 1/3 of the mass, so when the 3 of them are together forming a proton or a neutron, that accounts for the mass of the proton and the neutron both being 1. When a neutron changes into a proton, the neutron was in the nucleus and the proton is still in the nucleus, so the mass of the nucleus hasn't changed, which is why in beta minus decay there's no change to the mass number from the original radioisotope to the newly formed isotope. So here our radioactive lithium is unstable because it has too many neutrons. When a neutron changes into a proton because a down quark has changed into an up quark, the newly formed beryllium has the same mass number. But something is emitted from the nucleus, and that is this high energy electron, the beta minus particle. So this high energy electron is emitted from the nucleus, and this happens to conserve charge. The neutron has no charge. This is because the down quarks that make it up both have minus 1/3 of a charge. But the 1 up quark there has a plus 2/3 charge, so overall the charge is 0. The proton that's formed by the change of flavour of the quark produces a minus 1/3 and 2 plus 2/3 charges. so overall the charge of the proton is +1. Therefore, a -1 charge has to be emitted from the nucleus to make sure that charge is conserved, that it's 0 before and in total after. So, the high energy electron is emitted from the nucleus as the down quark changes to an up quark and the neutron becomes a proton. Radioisotopes that are above the curve of stability are unstable because they have too many neutrons. To become stable, they will emit beta minus particles. They'll emit high energy electrons from the nucleus of their unstable atoms as they change into a new, more stable atom as a neutron changes into a proton because a down quark has changed to an up quark inside the nucleus. As this happens, charge is conserved. The total charge before is 0 of the neutron. The total charge afterwards is 0 because the ejected -1 charge balances that +1 charge of the proton that's now left behind. And remember that mass is conserved too. That's beta minus decay. There is another type of beta decay though, beta plus decay. It's time to think about those positrons. So now it's going to be time to pause the video. Grab yourself a piece of paper and a pen. I want you to try writing down where you think you would find beta plus emitters in relation to the curve of stability. Why are these unstable? Why are they not on the curve of stability? What changes into what to make it more stable? What flavour of quarks changes? Is mass conserved? Is charge conserved? What is emitted from the nucleus? Just apply the knowledge from the first part of the video to test yourself before watching the second part of the video to check you're right. Welcome back. Do you know how tempting it was to slide in the full version of my song at this point? But I think the video might end up a bit too long, so you're safe. Let's see how you got on. So now we're talking about beta plus decay, we need to talk about positrons. Positrons are emitted from radioactive isotopes that have too few neutrons. They don't have enough neutrons to be stable. To become more stable, we need to move nearer to the curve. So a proton changes into a neutron in beta plus decay. This brings the radioisotope up and in towards the line of stability. As a proton turns to a neutron, an up quark changes to a down quark. As this change of flavour happens, mass is conserved. If the positron wasn't emitted, then charge wouldn't be conserved. But because the positron has a charge of +1, this does conserve charge as a proton becomes a neutron. And that's it. Both types of beta decay. How did you do on your beta plus ideas? If you're up for it, we could extend it just a tiny bit by adding in another fundamental particle, the neutrino, and its antiparticle, the antineutrino. In beta plus decay, as well as the positron being emitted, there's also a neutrino emitted. In beta minus decay, as well as the high energy electron, an antineutrino is also emitted. And that really does bring us to the end of our beta minus and beta plus beta decay revision video. You know that
regular review gets a better grade for you.
Don't forget to
Like,
so that I can keep making the videos.
comment,
Especially to request other revision topics.
subscribe.
So you can get notifications of when my next video gets uploaded.